Yes, yes, it clear. Just make the full screen.
Yeah, I just tried it, but it doesn't
Yeah,
work.
just
Perhaps
yeah,
now we have the full
yeah, very
screen.
good now.
Now we have the full screen. Okay, so one moment. So I'm pretty sure I don't have to introduce myself.
Yes, yes,
So
no need to
I'm
introduce
very
you. You are session
no,
chair, so just go
no.
ahead.
So I welcome you to my presentation on the grading of oil palm lumber. In the next 15 minutes, I will introduce in the grading with X-ray, ultrasonic testing, and natural frequency measurements. And I will show the chance to upgrade the inhomogeneous raw material to produce better products. Lena presented our first glue laminated timber from oil palm wood and its properties. Big challenge are the defined properties and the product optimization. In our case, competitive elasto-mechanical properties as well. Comparable, no, sorry. A big challenge are the defined product properties for the product optimization. And in our case, the big challenge were the elasto-mechanical GLT properties in the strength class system. And therefore, the lamellas must have defined elasto-mechanical properties as well, comparable to the strength class system for softwoods and hardwoods. And the same principle is valid for all other products like blockboard, multi-layer boards for furniture or interior design. For many properties like the MOR and the density of GLT and CLT and their lamellas, the determination of the characteristic values is based on the 5th percentile. In my first presentation today, I've shown that the properties of oil palm wood are varying extremely compared to common wood species. Without grading, according to relevant product properties, the 5th percentile, for example, of the strength, is very low. Too low for market competitive products. Therefore, grading is without alternative. Oh, sorry. All elasto-mechanical properties depend on the height within the trunk because the cells at the bottom are much older than those at the top. The cell wall thickening during the lifetime of the cell results in better properties of the older cells. Therefore, older oil palms have better properties at the same position than younger palms. This is one reason why coconut palms, there will be a presentation on Thursday, have better properties than oil palms, because coconut palms become much older. The position within the cross-section at a certain trunk height has an influence on the mechanical properties. This is because the number of vascular bundles per unit area and the area proportion of the vascular bundles is rising from the center to the periphery. Therefore, the density and the mechanical properties are rising from the center to the periphery of the cross-section. But without knowing the age of the palm and the position along the height, the number of vascular bundles per square unit or the share of vascular bundles is not a sufficient grading criteria. And the density is much easier to determine than the number or share of vascular bundles. Compared to common wood species, the correlation between strength, stiffness, and density are very strong. There's a power law relationship with high exponents compared to softwoods and hardwoods. This shows the great effect of density variation on strength and stiffness. Because of the strong correlation between modulus of elasticity and strength, non-destructive grading with ultrasonic testing or vibration methods, which determine the dynamic MOE, is an option. We've seen almost the same slide before. Because the property gradient within the cross-section, the peripheral boards show a great property variation within one board. This diagram shows on the y-axis the density profile over 160 millimeter width on the x-axis of a peripheral board. Direct under the cortex, as Lena has shown, the density is 800 kilogram per cubic meter, which decreases very steep within the first 4 centimeter to 300 to 350 kilogram per cubic meter in the board center. The outer 20 millimeter and the cortex are missing on the right side. In this example, we produce glulam lamellas with a width of 50 millimeter, which is very small for glulam production. On the left diagram, the 50 millimeter lamellas are cut from the periphery only according to their geometry. In lamella A, we would have a density gradient from 800 kilogram per cubic meter on the left edge with a tensile strength of much higher than 35 megapascal to 350 kilograms per cubic meter at the right edge with a tensile strength of 7 to 8 megapascal, less than 1/5. This lamella A is far away from a homogeneous lamella in regard to its properties. On the right, the same lamella is ripped according to the density profile in stripes with individual width and homogeneous density. In our case, stripes in 4 density classes A to D. The width results from set density limit values. For lamella production, the stripes are edge glued and cut to a width of 50 millimeter, as Lena has shown. Depending on the limit values of the density, the ripped and glued lamellas have more or less homogeneous properties. As more density classes, as more homogeneous the lamellas. But how can we measure the density over the board width for ripping according to the density? The most appropriate method to determine the density is X-ray along and across the board length. The absorption of X-rays in materials is directly related to the material density and dimension. If properly calibrated, existing X-ray devices can be used for oil palm lumber. Along with the X-ray absorption rate information, it is necessary to know the dimension and a homogeneous moisture content is needed. For Lena's GLT test specimens, the density gradient was measured on both ends of the boards using the Dance Lab X from Electronic Wood Systems. This measuring device is designed for the determination of density profiles of wood-based panels in the lab. The device got a special calibration and raw data filtering for oil palm wood. For various boards, we compared the density on the y-axis over the board width, on the x-axis, determined by X-ray, the red line, with gravimetric measurements, the blue line. Both showed a very high correlation. On the peripheral boards from the first trunk section, the density at 3 meter height is much lower than that at 0.5 meter height and is therefore relevant for the ripping positions. Because, as Lena said, no grading standards and no strength class system exists for all palm lumber, the strength grading classes for softwood according to the European standard was used. Because the lowest strength class is C14 in the standard, characteristic values for the strength class C10 and C12 were extrapolated. For the calculation of the forecast limits, the statistical correlation model according to the European standard was used. With the regression functions between the elasto-mechanical properties and density shown in my first presentation today, the density limits were calculated for tensile and compression lamellas in C10 to C24. For Lena's GOT, we used the density limits for C10 and C14 for ripping the boards. Lena showed that the glulam beams met the requirements for construction timber in regard to bending properties. The beams from ripped lamellas showed higher MOR and MOE. Ripping lamellas according to the X-ray density upgrades the raw material. Prerequisite for density grading is that the height within the trunk is known. At the moment, we optimize the density limits and will produce and test much more oil palm GLT together with the colleagues from FIDEC. The applicability of ultrasonic and natural frequency measurements for grading purposes of oil palm wood were evaluated by comparing the dynamic MOE from ultrasound and longitudinal and flexural vibration with static MOE from a 3-point bending test. 120 small-sized specimens were prepared from dry material. Ultrasonic time of flight measurements in longitudinal direction were carried out using Steinkamp BP5 with plane and conical probes for longitudinal waves with 50 kilohertz. Coupling was performed directly without a coupling agent. The dynamic MOE was computed from ultrasonic speed and density. Natural frequency measurements are state-of-the-art in the industrial inline production for grading. The natural frequency of longitudinal and flexural vibrations was determined using grindosonic MK5. Longitudinal vibrations were used to compare the ultrasound sound results. Flexural vibrations were determined to illustrate the differences between respective vibration modes and for the comparison with the 3-point bending test. Impulse was initiated using a small impact hammer. Dynamic MOE was calculated from natural frequency, density, and geometry. The 3-point bending tests were carried out for comparative purposes. The correlation between the ultrasonic velocity on the right axis and linear regression number 1 with the MOR on the x-axis, the frequency from longitudinal vibration on the left axis and linear regression number 2, and flexural vibration linear regression number 3 and the MOR on the x-axis are strong. The linear relations between dynamic MOEs and standard MOE are very close. The MOE from ultrasonic measurement, it's the number 1 on the y-axis, and longitudinal vibration, the number 2, show higher values compared to the static MOE on the x-axis. Higher values of the dynamic MOE determined with ultrasound compared to the dynamic MOE with natural frequency measurements are caused by bulk density gradients within the test specimen. Higher sound velocity can be observed in the area with the highest permeability. In the case of oil palm wood, the fiber caps of the vascular bundles. In contrast, the anatomical structure affects only marginally the natural frequency because the specimen vibrates through its entire specimen. The dynamic MOEs on the y-axis in this diagram show a higher correlation to the MOR than the density, frequency, and sound velocity. Therefore, the dynamic MOE can be used as strength grading criteria. Because of the property gradients within the cross-section, ripping the lumber according to their geometry from the periphery and grading the stripes according to their density from mass and volume is absolutely necessary. Furthermore, it is advisable to rip the board lengthwise into stripes based on density using X-ray measurements. The stripes should be graded according to their density and, if the height within the trunk is not known, their dynamic MOE. Afterwards, the stripes are glued together based on their properties to produce laminated elements. Ripping lamellas according to the X-ray density upgrades the raw material. But for industrial application, an inline X-ray measurement device is necessary. In general, both ultrasonic and natural frequency measurements in longitudinal and flexural vibration are suitable for industrial strength grading of oil palm lumber. Longitudinal vibration seems well suited to determine the dynamic MOE of dry, large-size specimens in component dimension in an industrial production environment. For an industrial application, the inline implementation of natural frequency measurements is less complicated than those for ultrasonic devices. But a high-speed inline system for industrial application needs to be adopted. Many thanks for listening and for the research funding. And I would like to thank Electronic Waste Systems for their lab and my students for their lab work.
If any question, you can ask with her, otherwise she can continue her session chair job.
No questions?
Yeah, no questions.